Hello. Thank you all for coming. Welcome to my talk. I call this talk Understanding Principles of Rx, React, Flow, and More Through Programming Principles. And I understand it's a very long name, so apologies if it's like very generic. My name is Victor. I'm an Android engineer here at Square in San Francisco. I've been at Square for 5 years, and my claim to fame is that I've dealt with a lot of bad Rx code as we've shipped the last 5+ years. So I've had to kind of unwind and trying to learn exactly what have been all the problems with all of our bad code, and then try to explain it to people as we perform refactors. So what to expect in this talk? So we'll start with the table of contents, which is this slide. I'll give an overview of just this talk and all the problems I've been facing. And then we'll dig into some of the areas I've been trying to figure out a way to explain RxJava, reactive programming, all those words. And so we'll explain what is a computer, and then we'll get into programming paradigms and what it means to write stronger abstractions. And so my ultimate goal today is to give you a different lens to view programming. I think that's like the most interesting way I've heard of talking about programming is to sharing programming is everyone has different lenses, and the more that I can give you a different lens, you'll take away something to move slides. And it's also to get you excited about programming paradigms, because I think we keep hearing these word programming paradigms, and I don't think we actually know what they mean. I think we hear the words like declarative programming and imperative programming, and we kind of have a loose sense of what it is. And it's actually a very interesting world. And my journey into it was my coworker just gave me this 15-page PDF, and it's just like, read it. And I was like, great, actually, this is like the most interesting thing I've ever read. And the last thing is that so a lot of the stuff that I'm gonna be talking about is my kind of interpretation of it, because I think the academic interpretation of like a lot of these like programming paradigms isn't very helpful or useful, and kind of slightly nonsensical in some ways. So let's start off with like very simple code. I think like everyone can like see this code and understand it. Hopefully you can. Okay, I'm sorry if you can't actually understand this code. So what we have here are, well, I would say everyone can see there are functions, and then there's this imperative block in the middle. And I think we all know the words functions, and we all know the words imperative, and then we all know the words imperative programming, but then you start going like, what's functional programming in this context? How can you just have imperative and functional code at the same time? So even between at like this basic level, so basic level of imperative versus functional programming, I don't think we have a very good vocabulary of explaining what are the differences. So how do we even get to the point where we explain what is reactive programming versus functional reactive programming? And then there's a whole other question of like, does it even matter? What's the difference? So forget everything I just said, and let's just build a computer from totally first principles. I think we've all heard of Silicon Valley, but like, what is silicon? So this is like the first principles I'm going back to. So silicon is like a very unique property in that it's like one of our most abundant elements, but it has like 4 electrons. And through the smartness of like a lot of scientists, we realize we can do something pretty fun, which is if we put phosphorus in there. Phosphorus has 5 electrons, and what it's gonna do, it's gonna kind of like electrify this sheet of silicon. And then you can think of, let me make sure this animation goes. So that was phosphorus, which has 5 electrons here. Then there's also boron, which has 3 electrons here, and that's gonna like imagine unelectrifying silicon. So some very smart people realize that if you put all of these next to each other in kind of like this fashion and wire them up in even more complicated fashions with resistors and things, you can develop what we call is a transistor. And the cool property of this of a transistor is that if you apply a voltage to the middle of that, so it's called the base there, if you apply a voltage to the middle there, it actually will allow the current to flow. But if you don't apply that voltage, then the current won't flow. And so that is actually, so this sheet of thing is actually simplified into this like low transistor. You've probably seen like this 3-prong transistor around, like quite around there. So why do I talk about transistors? So the next step in transistors is once you have a transistors, you can start building logic gates. So if we take this transistor and like look at the top right diagram, we can kind of represent this whole flow using this like little transistor diagram over here. And if you're cool and you want to start building a computer through it, you can take these, you can wire up your logic diagram like on the left here, which equivalently looks like the breadboard on the top left. And this is actually an AND gate. So this is an A and B signal here that's wired into your transistor, and the output here is this line over here. So you can build effectively, so we just went from effectively silicon to a logic gate, which is kind of crazy in my mind. And so you can do this with everything, right? Like you can start building OR gates, which is crazy. And if you start mixing all of these together, we know that there's like AND gates and XOR gates. You can build an adder, which takes in like pluses, and then you'll come out with like sums and a carry out signal. Which is like, we're going from silicon. One of the cool things that we realized you can do is if you take the output and wire it back into the input, that's gonna have some cool properties that we call latching. And so if you do that in, again, more and more complicated ways that some smart people in the past figured out how to do, you can build an SR latch. And the cool thing with an SR latch is if you go even more complicated, again, add even more things to this thing. This is a timer. So this is a capacitor that will discharge and then recharge constantly because of how we set up the resistance curves. We could run half courses on like a lot of these topics, so I'm like zooming forward. So what was the cool thing about clocks? So the reason we have clocks is that we're fundamentally running with circuits, and there's going to be propagation delays for whatever happens. And so what we use clocks is to kind of manage that propagation delay. Keep going forward. So imagine you were building this from a breadboard. This is possible, and this is a real version of that. Now, taking another huge leap forward with the help of people, with all of those things in place, we can start building a whole breadboard, a whole system. And this is, if any of you have like taken like computer engineering courses, this is essentially a simplified computer architecture. And so hopefully with some of you, if you know how computers work, this is kind of maybe a review. But how computers work is there's a program counter that's going to have the address. And then so it's going to point to like 0000. And then at the next step, it's going to load the address into the IR register, the instruction that's at 000. And then it's going to compute it, and then it's going to increment. And that's how computers kind of work. So those instructions can look like something like this, like binary and addition constructions to like kind of move memory or add and subtract variables and registers. And again, huge leap of abstraction again. On the right is a C program, and on the left is the sequence of load and like address instructions that it would assemble into, essentially. So the left is called machine code, and the right is kind of like the things that you and I would write day to day. And basically, this is the whole of how programming works, right? Is that all of the code that we write on the right-hand side gets assembled into this machine code. This machine code gets written into RAM. This RAM gets executed by our program counter, and et cetera, step by step, continuously. So that was silicon to programming in about 5 to 10 minutes. So why did I go through this? we went through essentially silicon, transistors, logic gates, circuits, and then machine learning instruction sets, programming languages. I like to view these as layers of abstraction, right? So like, we developed one of these layers, and then every layer we figured out some way to make it even more abstract so that we could like share it or like simplify it. And you can kind of view transistors, right? If you're refining a transistor, that abstraction, you just get maybe make smaller transistors or maybe different transistors. But if you increase the level of abstraction, you kind of get logic gates. So we apply this to programming languages, which is cool. So if you refine a programming language, you build abstractions in that programming languages, and you build paradigms, so ways to like view that abstraction. And then you could think of also increasing that programming language abstraction. What does that look like? No code, maybe? I think spreadsheets are a really cool example of increasing that. So you kind of would fit like programming paradigms and abstractions in that kind of layer. And then why else did I kind of explain about computers, because that was a lot of time. I think one of the coolest things in my mind is that computers are imperative. We just went through that a computer is executing line by line these machine instructions. But then we also call this whole thing called programming paradigms also imperative, right? And actually, I think that is actually very related. I think you can kind of view imperative as this like way of writing code that's exactly line by line, telling the computer exactly what to do. And then you can kind of explain declarative is just everything else on top of that. So that's your gradient. So you have imperative, which is like bare metal C machine code, and declarative is everything else. And I think rethinking what that means to be declarative, it really helps you to like crystallize what abstractions are, and like be okay just living in a world of very abstractions, of very abstract. So the point of declarative is that we can kind of hide a lot of the implementation details of things, and if you kind of think about it, the more declarative you can be, the easier it is to kind of get a fuller understanding of the sense, because you don't have to be bogged down by the tiny implementation details. So returning to that original function that we had, we start with like functional, and so we can definitely see the layers of abstraction, I feel like, a little bit better. So we have these imperative details that are inside the function, but once we have the function, we have like this more declarative way of explaining that code. So it's just like a different declarativeness based off of how you kind of view the instruction. And it can maybe help to think like interface versus implementation detail. That maybe helps. And then we can go like way too far, which is like Excel, which is a spreadsheet, right? Which is like every cell is a declarative sense. There's like no imperative code whatsoever. It's all declarative, but it's declarative in like one specific way. So hopefully I've convinced you that like declarativeness is like kind of like a gradient. So this is actually, so the first thing I'll challenge is object-oriented programming imperative? And so I think after this, you can kind of, we kind of always have said that it's imperative, but I would say that object-oriented programming kind of declares objects have functionality, and then you would wire this functionality together imperatively, but there's still some declaration of that an object has functionality. And so, yeah, so this idea that when you declare something, it has like a contract to be fulfilled. And then slightly tightening that, we invented kind of rules to increase the declarativeness of this imperative-ish paradigm in OOP, right? Like we've invented like these solid principles, and we kind of say that like for single responsibility, if you have an object do less, then you can declare its behavior better. If you have like open close principle, if you add a new behavior to an object, you should make sure that the object supports that behavior rather than having to modify that behavior. And so you can kind of apply these for all all of our like rules. And that was like one of the like coolest things in my mind as I was trying to figure out how to explain to people like why even bother about solid. It's because there's like value in this declarativeness. So from that section, so hopefully we can get away, we've like gotten away with declarativeness as kind of this gradient. And you like build abstractions in your mind about how declarative or not declarative your code is, and we think that more declarative code is more valuable. So let's go into a little bit with like programming paradigms and like a little bit more formally. So on the left here we have Kotlin, and on the right we have Scheme, which like most people say is a functional language. So there's something called records, which is an actual feature of programming paradigms. So you can see on the left and on the right, they both support this concept of records, right? So a record is just like a reference data. So imagine in the past, if you didn't have like a name to reference data, you'd like be talking about like an address constantly. So being able to reference data by a name is like a higher level of abstraction. So same thing with something called closures. Closures are a feature, it's supported in both languages. Again, in the past, if you didn't have a closure, you'd be writing like a goto, right, imperatively. You'd be calling a jump statement. So jump to this address instead. So a higher level of abstraction. So something cool is that in Scheme, they don't really support like mutable variables. So there's something called name state, which is a feature. And you can think of name state as state over time. And I think this was a very cool thing. It's called variables because it's variable state over time, which is really cool when I first learned about that. So with like these features, and like you can add a ton more features, you can kind of build a taxonomy of how to program based off of like the kind of different features that you have. Of course, like the interesting ones are like in the middle here and on the right here for us like Android, like Java developers. It's like how do you, like you see the word functional reactive programming, don't look too hard, and shared state programming. Hopefully that was like pretty fun, and the slide is like kind of one of the reasons I like get up at night or keep up at night. Let's talk about a bit about concurrency paradigms, because I think this all gets like super interesting once you add concurrency into the mix. With concurrency, I think and this whole declarative sense, I think we would like this idea to be able to declare that our code was concurrent rather than actually like write the concurrency ourselves. Because like if you think about it from like a very Java old school standpoint, we kind of just pretend we're the CPU and we pretend we're a thread, and we like put this work on this thread and then put this work on that thread, and then try and like manually manage all of these, like the state that's going on. Just for example, if you look at this code can't be accessed safely in a multi-threaded manner, right? Because you will get a concurrent modification exception. That color is very dark. That's this concurrent modification exception. So you have to do something called like synchronized, right, in Kotlin, which is now deprecated, so it's kind of a crazy thing. So this kind of programming, we call this shared state concurrent programming. So so you can see the word like shared state is the whole idea that you have a shared resource, and then you use threads and then you have to lock the resource as you go around. So with Java executors, and I think as everyone who's written in like schedulers and Java executors knows, like it's so hard to have confidence in what you're writing and the correctness of your code even. So you kind of have to have like single-threaded schedulers all the time everywhere. There's a paradigm that's called message passing concurrent, which is if you just have single-thread components, single-thread receives, then you can kind of guarantee the order of things. So you can see this is kind of like an implementation of that, but it's like single-threaded, right? Like so you're losing a lot of the like benefits of concurrency. Now we get into some of the fun and more like fun ones that maybe you haven't heard of. So continuous synchronous programming. So imagine this idea that time doesn't exist at all, and anytime you did anything, you instantly had the answer. That kind of just looks like a math equation, and I don't think anyone actually writes code like this. I hope if you do, like, let me know, I guess. Imagine you wrote your program. This is an animation for a bounce that you were just like describing the coordinates of the bounce through like this kind of like lambda-ish, like monad-ish syntax. The cool thing is that this thing that I call continuous synchronous programming, that's just functional reactive programming. For some reason, I think normally you start from functional reactive programming and then you'll learn it's continuous synchronous programming. But in reality, functional reactive programming is just a like alias for continuous synchronous programming. So if we get into like discrete synchronous programming, where you're programming kind of like the digital circuits that I described earlier, where you have like a distinct clock tick every point in time, that is actually called reactive programming, which is pretty cool. So the thing that we can today talk about as RxJava is reactive programming, but you would really more formally call it discrete synchronous programming. And how that works, we can like dig into that like a little bit, is that when you have a Rx operator, the stream and the source, the source and the observer kind of just give you this guarantee that the same inputs will always have the same outputs, and that's how you. That's like the declarative aspect of it, right? Like we are just trusting that this library is giving us this concurrency guarantee. What that kind of looks like is, in reality, if you have like two events coming in, and one of them is like slightly ahead of the other, there's gonna be, to progress through, they're gonna like clock tick through like that, and there's gonna be no scenario where one of them is gonna operate ahead of the other one accidentally. And that's kind of like a guarantee that the Rx library is giving you with respect to concurrency. The last concurrency thing to like think about is we have this thing called continuation programming, which is effectively calling coroutines, but you might have seen it as like exceptions. Exceptions are a way of like how continuations also work, and sort of like go-tos. So one of the things that continuation programming is, it's not actually a very declarative paradigm. Like with coroutines, you're actually just like imperatively still writing a bunch of code and just embedding very like lightweight threads of operation in that imperative world. But I think like the reason that we like it so much is that like our brains have been wired like imperatively from like just like everything that we've ever learned. So it feels it's just much more natural. So hopefully that was like an interesting like weave through some of these. There's like so many more paradigms to like think about and just like be interested in about. But not that much actual literature trying to like make it accessible to like Java developers or like to normal lay people. So one of the things that maybe I talked through is, so are we done? Like I just like said that we have RxJava, we have like Kotlin Flow, which kind of feels like RxJava. Do we like have all the tools that we already need to write like perfect, great code, declarative code? So I think there's like this concept of like misusing patterns. So this is my RxJava refactoring level. So I think if you've written RxJava and you've seen this code, there might be some things that like stand out to you, going like, what is going on in this code? So one of the things is that a single Rx stream is deterministic, but once you have multiple Rx streams, like what is the behavior that is like, I can't even like describe it, right? So this single stream is like not super deterministic, but I guess if you wrapped it in this other stream, then like you could ignore that this single stream wasn't deterministic, and then that this bigger stream, there was some pattern that it's emitting. You'd have to like unit test it to like figure out what that is, but it would be deterministic in the larger sense, perhaps. So if we wrote our applications as a single Rx stream, maybe we could have like a deterministic app, right? And be confident in that. But probably no one's written that, or like you're getting pretty close to doing that maybe with like a Redux or I don't know, necessarily know. So how do we reconcile that we're using this declarative paradigm in a way that actually just reduces its declarativeness, right? By like having these weird things. So yeah, I think we should differentiate a little bit by like what is a paradigm and like what is like the abstract sense of a paradigm, and kind of like how does a language implement a paradigm, right? Because different languages may implement different paradigms differently. So I went back to this like Kotlin versus Scheme example. In Kotlin we can call, what happens? In Kotlin, we can have like val instead of var, right? And var like allows us to have a mutable variable. But in Scheme, like that doesn't really exist. Like by default, you have to go into like the documentation and go figure out that there's like a set with an exclamation mark, and that's like trying to say like don't call this function because there's an exclamation mark, which sounds oddly familiar with Kotlin. So there's this idea that some language can like discourage mutability and discourage breaking the rules that it's setting out in its language design. So of course, that means that if you do that, you can make it harder to make mistakes and harder to break your abstraction. If you've seen RxJava code, this also is like one of my favorite bugs to see all the time, which is that this is calling get value and then returning single.just that value. Like what it should be is calling from callable and then calling get value only upon subscription, right? So the problem with Rx is that there's like a lot of these rules to keep it, Rx has like a lot of rules to keep it safe to use and keep it like declarative and deterministic, but how are you supposed to know that? So this is not limited to Rx, right? Like you can do this in Flow as well, accidentally. This is the exact same problem that you get with Kotlin flows. That kind of goes away if you use like coroutines, right? Like if you just use coroutines, then you don't, there's no way of making that mistake at all. And then we can also think about how you can't even start calling coroutines without a coroutine scope, but in RxJava you can just call subscribe everywhere. So I like to think of like a strong like paradigm, or maybe just like a strong abstraction makes it difficult to kind of make the mistakes that would break you out of the rules of that abstraction. Especially because sometimes you don't even know what the rules are to start with. Yeah, so exactly like why are we, like who's telling us no to do this, and then like why are we allowed to do this? It's kind of the problem. And reality is Java is just very flexible if you kind of think about it. Like we're implementing this like whole crazy pattern, new pattern across like all the basically imperative languages called like reactive streams, right? And we're just implementing it in a declarative, in a fundamentally imperative language. So you can kind of think there's like analogies for like solid for RxJava and Flow, right? Like you can apply like dependency inversion to Rx streams or Flow streams, right? Like where all the events in your stream should be at the same level of abstraction. Maybe for S, it's like don't put side effects in like your flat maps and like switch maps. Put them in your subscribe. Try to have like one stream at all when you can. Use like L-safe bridges to interact between the imperative and reactive world. I think one of the things that I try to like get people to use way more often is if you have a listener converting like a listener pattern to a Rx pattern is like as simple as just like writing this like 6-7 lines of code, but people don't, people aren't aware of the, just like the different ways to kind of like mingle. So I think the lesson I try to come out with this is that in a lot of the patterns and like codes that you're using to like be aware of like the declarativeness and like how to use the pattern and like keep to maintain the advantages of the pattern. And you can kind of apply this in some of the other things, right? So like what are rules for other programming paradigms like coroutines, right? Do you want to emit into a flow while you're in a coroutine that you're collecting? Like, I don't know, maybe. And then even more abstractly, what are the rules for your like architectures and libraries, and how easy is it to break those rules accidentally or incidentally? And so the last part to like kind of like think about is like what is kind of the next programming paradigm. So I think we invent like paradigms all the time, and we're not like thinking about it anytime we're like implementing a new architecture or kind of just like solving a generic problem, because really paradigms aren't really like, I think we take the word paradigm too seriously. I think we think about it more as abstractions. So what are the new abstractions we think about? And then I think from all of this, for most of this talk is like, as we invent our own abstractions, how can we make them more expressive, more deterministic, more declarative? And that's how we view it as like a strong abstraction. And then when we use an abstraction, how do we use them safely to maintain also their declarativeness? Cool. So that is it for my talk. I think there was a lot of material in this things. I think if there's any one thing that I would love you to come away from the talk with, it's that there's this PDF that's like 15 files large called Programming Paradigms for Dummies. It's kind of like an annoying title, but it's actually a really great introduction to programming paradigms. If you like the part about building a computer, I would super recommend watching this dude's YouTube series called Building a 8-Bit Computer from Scratch. And then a lot of the materials and ideas I referenced are kind of like sourced from Conal Elliott, who was actually the first person to actually term the word FRP. And that is it for me. Thank you.